A single integral solves them all. So over here I have a king integral at the top of the screen, which when I solve it, all the 6 integrals that are over here in the bottom will be automatically solved. So first of all, let me show you how this integral can solve the other ones, and then at last we will solve this integral. Okay, let me do it. So we have integral from 0 to infinity of e to the power minus pt square minus q by t square dt, and this one is equals to 1 by 2 root under pi by p e to the power minus 2 root pq. Okay, now once I solve this integral, I can put q as 0. If I put q as 0, I will get the following integral from 0 to infinity of e to the power minus pt square, and this one goes to 0 dt, and then is equals to 1 by square root of pi by p, and since q is 0, over here this will be e to the power 0, which is just 1. Now from here I can actually find the values for both this 1 and number 6 integral. How? If you ask me how, so what you need to do is just substitute p as I. Substitute p as I, over here we will have integral from 0 to infinity of e to the power minus I t square dt, and we know that e to the power I theta can be broken as cos theta plus I sin theta. So we will use this formula to break the integrals into two parts. And in the right hand side we have 1 by 2 square root of pi by I. Now using the Euler's formula, I can write I as e to the power I pi by 4. So e to the power I pi by 2. Yes, and if I now take the square root, this will be root pi by 2, and then 1 by e to the power I pi by 4, and when it goes to numerator it will be e to the power minus I pi by 4. Yes, now let me break this into two integrals. Integral from 0 to infinity cos of minus t square dt plus I sin I integral from 0 to infinity of I sin minus t square dt, and we know that the sum of these integrals is going to result the following value, root pi by 2, and this is also cos of minus pi by 4 plus I sin minus pi by 4. Yeah, now we know that the real part and the imaginary parts are equal to each other. Yes, so over here this thing integral from 0 to infinity of cos of minus t square is just cos of t square, because cos is even function. So this one will be equal to the real part from here, root pi by 2 times cos of minus pi by 4 is just 1 by root 2, so that is root pi by 2 root 2. Similarly, the imaginary part from the left hand side, which is integral from 0 to infinity of minus sine of t square dt, this will also be equal to the imaginary part from right hand side, which is root pi by 2 times minus sine of pi by 4 is 1 by root 2. So now you can cancel the minus from both the sides and get the following result, that integral from 0 to infinity of sine of t square dt is also root pi by 2 root 2. So you see how that this integral, the single integral, can also give us the value of both the integrals. Now the first two are done. Now for the second and second last as well as third and third last, we will use the original integral without putting q as 0. Now in the original integral, where we have integral from 0 to infinity of e to the power minus pt square minus q by t square dt is equals to 1 by 2 root pi by p e to the power minus 2 root pq. Over here, now to get this first these two integrals, we can put p as I and q as minus I. Let us do that and see what happens. Integral from 0 to infinity of e to the power, if I take minus common, and this will be I times t square. Yes, and then if q is minus I, so plus of and then minus I by t square. Yes, and this one is just equals to 1 by 2 root pi by I, and since I times minus I is minus times minus 1, so that is just plus 1, so e to the power minus 2 times square root of plus 1. Now over here in the LHS we have integral from 0 to infinity, and for this one what I can do is take this as e to the power minus I and t square minus 1 by t square. You can write it like this, dt. And over here again you can also change I to e to the power I pi by 2 and then take square root I pi by 4 and take it up, so that e to the power minus I pi by 4, just as how we did earlier, and this is just e to the power minus 2. Yes, now over here I can again use the Euler's formula and break this integral into two pieces, just like how we did earlier. So this becomes integral from 0 to infinity of cos of, since there is minus times this expression, so for cos it won't really affect, yes, because cos of negative theta is just cos theta, but for sine we will get a negative sign, and the integral from 0 to infinity sine of t square minus 1 by t square dt. Yes, and all with an I over here in front, and this is equals to 1 by 2 root pi, and then e to the power we have minus I pi by 4 times e to the power minus 2. Okay, looks good. Now after this we can just compare the real part and real part, imaginary part and imaginary part. So for that I can just break this into two pieces, e to the power minus I by e to the power minus I pi by 4 as cos pi by 4, which is 1 by root 2, minus I times 1 by root 2. So comparing the real and imaginary parts with each other, we can get that integral from 0 to infinity of cos of t square minus 1 by t square dt. This will just be root pi by 2 root 2 times e square in denominator. Similarly, comparing the imaginary part, we get that integral from 0 to infinity of sine t square minus 1 by t square dt. Now over here we can see that both have the negative sign, so they actually cancel out, and we get this answer as root pi by 2 root 2 and e to the power minus 2 e square. So we have also solved the second and the second last integral, yes, with the same formula by substituting p as I and q as minus I. Now it's time for third and the third last. For that one we will just substitute I in for both the values of p and q. So let's see that. So again we will take the initial formula, original formula that we have, which was integral from 0 to infinity of e to the power minus pt square minus q by t square dt. This is equals to 1 by 2 root pi over p e to the power minus 2 root pq. Okay, now in this formula if we place both p as I and q as also I, we will get that third and the third last formula. Let us see how. So for this one we see that this quickly reduces to the e to the power minus I common t square plus 1 by t square dt, just as earlier. And over here it's 1 by 2 root under pi by, since p is I, and now e to the power minus 2 times, since both are I times I is minus 1, so this is square root of minus 1. Now this is just root pi by 2, and again I will be e to the power I pi by 2 is square to e to the power I pi by 4, and when it goes numerator e to the power minus I pi by 4, and e to the power square root of minus 1 is I, so minus 2I. Now in the left hand side we have integral from 0 to infinity of, now when I take cos of negative values it's positive, so it won't really matter, cos of t square plus 1 by t square dt. Yes, but for sine it will matter because sine is an odd function. That's why minus I times integral from 0 to infinity of sine t square plus 1 by t square dt. Now from the right hand side this is equals to root pi by 2 times e to the power minus I times pi by 4 plus 2. Now again, just as usual, we will compare the real and imaginary part, which gives us integral from 0 to infinity cos of t square plus 1 by t square dt. As from here, the real part will be root pi by 2 times cosine of this argument minus of pi by 4 plus 2, which is just cos of pi by 4 plus 2. Yes. Now if you compare the imaginary part, we get integral from 0 to infinity of sine t square plus 1 by t square dt, which is equal to root pi by 2 times sine of pi by 4 plus 2. Please note that the negative sign did not matter, because in the both RHS and RHS we have negative sign, which effectively cancel out, and we get this value. Now let me just check the answer to make sure if it's correct or not. So yeah, root pi by 2 times sine pi by 4 plus 2 and root pi by 2 times cos pi by 4 plus 2. So we got all the answers using this main formula. But now, how does this main formula come? So let's try to derive the original formula itself, and then all the 6 results that we have derived using that formula will be automatically validated. So let's go for that. Now we have integral from 0 to infinity of e to the power minus pt square minus q by t square dt. Now what we will try to do is, we already have two constants p and q over here, so we will try to reduce this to one constant first, and then we will try to make some use of Feynman's technique or Leibniz formula, and then do something that can be helpful. So first of all, to reduce this p, what I will do is I will make a use of substitution that u is root p times t. So with this use of substitution, we will get something interesting. So that interesting thing is integral from 0 to infinity e to the power minus p times, now t square is just u square by p minus q by, now t square is just u square divided by p, and dt will be du by root p. Now 1 by root p goes in front because it's just a constant, and integral from 0 to infinity we have e to the power minus u square minus pq by u square du. Okay, looks good. Now the next step is to try to reduce this pq again into a single variable. So for that, what I'm going to do is I will let this pq as a constant. So let's say k be the geometric mean of pq such that k square is pq. Now I could have just let it as k, but the reason I have let it k square is such that while taking in the differentiation in the Feynman's technique, this will give me k square over here denominator, and which will again simplify the use of substitution stuff, which we will see in the upcoming upcoming time. Okay, so let me just go with the flow, and we will see why this actually works. So if we make pq is equals to k square, we get 1 by root p integral from 0 to infinity of e to the power minus u square minus k square by u square du. Okay, so now we have just one variable, and this seems somehow easier to deal with than what we had previously. Now let me let this integral as I of k, integral from 0 to infinity of e to the power minus u square minus k square by u square du. Now if I differentiate I of k, when this differentiation goes inside the integral, that will be partial differentiation. So that's why I will just have a differential with respect to k. Now since there is a function of e, so function of e remains as it is, and nothing will happen to it. Now for this quadratic expression, first of all minus u square will be constant while differentiating with respect to k, and the second term we will have minus 2k by u square, and du will be as it is. Okay, so now the next step is make another substitution such that these two things reverse out, and this k by u square get absorbed in the differential element. So let me make y is equals to k by u, because if I do that, I know that dk is just going to be minus k by u square du. So minus k by u square, this whole thing is going to be absorbed, as well as these two expressions are gonna be reversed. So let's do that. I dash of k will be equal to integral from 0 to infinity e to the power, now u is k by y, so minus k square by y square, and then k by u is just y, so minus y square, and 2 remains as it is, and then minus k by u square du is dy. Now I'm missing something over here. The something is I haven't really changed the limits of integral, which I should have. So 1 by 0, if it's positive 0, it goes to plus infinity, just the infinity now, and the infinity goes to 0. Good. Now using the reflection formula, if I have to change the limits of integral, I should get a negative sign in front of it. So that's why negative of the integral from 0 to infinity, also a 2 over here, which comes out as constant, and then e to the power minus y square minus k square by y square dy. Now notice that this integral over here is actually the one that we started with. Yes, I of k. So I can again say this as I of k and then do the remaining process. So I dash of k is actually just the minus 2 times I of k. Yes, now I can write I dash of k as di by dk. Yes, and then minus 2 times I. Now let me just make the variable separation method. Let me just make the use of variable separation method to solve this differential equation. We have di by I is equals to minus 2 times dk. Now if we integrate both sides, we will get ln of I as minus 2k plus c. Now we want to find the value of the constant. So for that, notice that if we substitute k as 0 in the initial I of k integral, if I put k equals to 0, we will just have the Gaussian integral over here. Notice that I of 0 will just be the integral from 0 to infinity of e to the power minus u square, and this one goes to 0 du. And we know that this integral is just root pi by 2. Yes, so therefore I of 0 is just root pi by 2, and that's a pretty interesting result to solve this integral. So now we know that I is equals to e to the power minus 2 by 2k times e to the power c, and when k is 0, I of 0 is root pi by 2, and since k is 0, e to the power 0 will be 1, so we get the value of e to the power c. Now if we put this value of e to the power c in the solution of our differential equation, we get I as root pi by 2 times e to the power minus 2k, and this is exactly what we need. So we have got the solution that I is root pi by 2 times e to the power minus 2k. So let us substitute this back from where we had paused the solution of previous question over here. So over here now we can say that this is 1 by root pi, and then root pi by 2 times e to the power minus 2k. Yes, again we can put the value of k. If we put the value of k, we get 1 by root p times root pi by 2 times e to the power minus 2 root of pq. So this is the solution that we were searching for. So let's see if that's correct or not. So 1 by 2 times root under pi by p e to the power minus 2 root pq. So yeah, it exactly matches the solution, and this was the integral that yielded us all the 6 results. So just the flow of the solution was like this. So first of all, we reduced the variable into a single one, that is k, and then we used the Leibniz method or the Feynman's technique to differentiate, and after differentiated, this terms of the polynomial actually reversed and yielding us the same integral. So the differential was equal to the initial integral, and that gave us a differential equation which could be solved to solve for I. So this was how we solved this integral, and using this integral, placing the values of p and q as I, as minus I, as zeros, we could see that a lot different integrals of cos and sines could be solved. So this was it. I hope you understood the solution and the process that we have gone through, and I hope it in fact helped you to get some new ideas about integrals and how to solve them. Hope this was helpful. Thanks for watching, and look forward to seeing you in the upcoming videos too.